Okay, so here's another video. In this video we'll be looking at non-geometric proof of the tangent circle theorem. So essentially what I'm looking at with the tangent circle theorem is proving the angle PBO for a circle is equal to 90 degrees. Of course, PB here is just part of the tangent to that circle, and O is the origin of that circle. And of course we're assuming that length PBO is going to be the radius. So what I've got as the first step for the non-geometric proof is to assume the unit circle y squared plus x squared equals 1. What we want to do from here is we want to implicitly differentiate it. So we end up getting 2y times dy dx. Of course, we're just using the power rule for that term and differentiating with respect to x, plus 2x equals 0, because of course the derivative of a constant is 0. What we do is we bring dy dx and put 2y in brackets to separate them, and we move the 2x to the other side of the equation, and in the process it becomes negative 2x. Now what we do is we move the 2y into the denominator on the other side, so we get dy dx equals negative 2x on 2y. Of course we can cancel that down, and we can get negative x on y as the dy dx. And you'll probably know this because of course the actual derivative of a circle which is centered on the origin will always be negative y on x when we're considering the slope of the tangent at any point around that circle. But of course, we're assuming the unit circle here. So now, because OB is the radius, and of course we know that the radius of the unit circle is equal to 1, we can say that point B is given by negative 1, 0. Because of course we got the origin O, we're assuming that the unit circle is centered on the origin as per the equation here. So we can assume that because it is the unit circle, and this is r squared value, and obviously the r value is also the same one, that this b value, which is to the left of the origin, is going to be negative 1, which is the x coordinate, and 0 because it's still on the x-axis. So we just imagine a Cartesian plane in there. So what we do is we actually evaluate the derivative. So we look at the dy dx when x is equal to negative 1 and y is equal to 0. So we evaluate that, and of course it's negative x on y, so what we get is negative lots of negative 1 on 0, which is 1 on 0. And hey presto, we've got something interesting happening here. We have got 1, 0, 1 on 0, so we know that because we're dividing by 0, that the slope is undefined. And again, this helps us with the original claim we're trying to make when you're thinking of the circle theorem. Of course, when you're looking at the geometric proof, you're considering the fact that that angle cannot be greater than that. But with this proof, you're considering proving that the actual slope of that tangent line is undefined, because when something is undefined, the slope is undefined, it is what's known as a vertical tangent. And that brings us back to the original theorem. So because the slope is undefined, we've got a vertical tangent. And as a result, we can then say that angle PBO is equal to 90 degrees, or if you like to work with radians, of course that's pi on 2 radians. But there's a little bit of non-geometric proof for the actual tangent circle theorem, which is actually the angle with the tangent and the radius there. And again, pretty simple and straightforward to follow. It's just the idea that we've got a vertical tangent on the actual side of the unit circle. Again, we could have this in any order. If it was on this side, it would be 1. We could have it up at this point. Any point we could have a B and a P, but we would always find that the actual tangent and angle PBO would be equal to 90 degrees. So thank you for watching this video, and I hope you enjoyed it. That's a little bit of non-geometric proof for the tangent circle theorem. Thank you.